Okay, welcome back. So today I want to expand on the evolution equations that we developed for curvature last time. So we will derive evolution equations for all gradients of curvature and then use this to get a criterion for long-time existence of solutions. So evolution of gradient of curvature, and recall that we had an evolution equation for the metric ddt of Gij equal to minus 2 Rij, Ricci flow, and then we had derived evolution equations for the Christoffel symbols that was given by the gradient of Ricci terms, and then from this we had derived ddt of the Riemann tensor, and this had turned out to be something like the Laplacian of Riemann tensor, and then quadratic terms in the Riemann tensor, and let me write these quadratic terms like Riemann star Riemann, where star means a linear combination of quadratic terms in the Riemann tensor. Because for the evolution equation for the gradient of the Riemann tensor, it will only be important to have the general structure of this evolution equation rather than to have the precise form of every single component. So once we have this formula, it is clear that ddt of the gradient component, say gradient I of R, J, K, L, M, will have a leading term that comes from taking ddt of the Riemann tensor, so we will have the gradient of the Laplacian of R, J, K, L, M, and then plus these terms that are quadratic in the Riemann tensor. But then there will also be a term involving ddt of the Christoffel symbols of the Riemann tensor when we do this computation here. So there will be an extra term which involves the gradient of Ricci multiplied with terms involving the Riemann tensor. And now, once we look at this term, it will be interesting to exchange here the di with the Laplacian, because we would like to have a heat equation again for the gradient of curvature. But then this commutator of third derivatives will involve terms like curvature applied to the first derivatives. So there will be terms like Riemann tensor gradient of Riemann. And similarly here, when the gradient falls onto the square, we will get also terms that look like Riemann times gradient of Riemann. And finally, this term is already in the form gradient of Riemann times Riemann. So this is the structure of all the extra terms that we get. So here is already the general evolution equation of the gradient of the Riemann tensor. That's the structure we wanted. And this means in particular that we can estimate, when we now take the square, so let's already fix this result. Well, that is not the optimal optics here. You can see that. So let's write this ddt of gradient R, J, K, L, N. Let's write that into a box. So we have this structure of the evolution equation, and then from this we get immediately an evolution equation for the square. So we get ddt of gradient Riemann square will be the Laplacian of the gradient of Riemann square. And then from this product here we get the correction term, sometimes called the Bochner term. And the Laplacian, one factor falls on this gradient, the other on the other gradient, and we get minus 2 gradient Riemann squared. And then the extra term that we have there will have the structure Riemann times gradient Riemann times gradient Riemann. Okay? So we have a way of estimating the time derivative of the gradient length of the gradient of the Riemann tensor in terms of the Laplacian, this good Bochner term, and then something which is quadratic in the gradient and linear in the curvature. So, in particular, if we are in a situation where the Riemann tensor is unbounded, then this is a very bad term, whereas if Riemann remains bounded, then this is the same size as the term that we are estimating here. Now, in the next step, we can use just induction to compute higher derivatives of the curvature. So let me just state this result by induction. We can show that ddt of higher derivatives of the Riemann tensor squared can be estimated by Laplacian of the same term. Then we also get the Bochner term as before. And then we get lower order terms, but they all have the structure that you have lower order derivatives and you can count the orders because this inequality has to be scaling invariant. So depending on n, you get terms here that depend on the dimension and on this number n, such that we have some terms that always involve the nth derivative of the Riemann tensor. And then we have two more factors, but in such a way that the derivatives of these factors add up to exactly n. So I plus j, the order of derivatives that we get on the right hand side, add up to m. So for example here, the term that we get, n would be equal to 1. So we have one term like this, and then one of them is 0 order and one is order 1. So this is the general a priori estimate you would get of inequality for the derivatives of the Riemann tensor. Now, once you have these estimates, how to estimate the time derivative of the higher order derivatives, you can show that, as you can already see here in the order 1 case, once the curvature is bounded, then these other terms are of the same order as here. So this means if the curvature is bounded, we get the first derivative bounded, and then using this, from the first derivatives, we also get all the higher derivatives bounded. In other words, nothing can go wrong anymore once the curvature is bounded. So this leads to the result, which I state now, that as long as the curvature is bounded, the flow can be extended further into the future. So here's the theorem. Assume that Gij of t is a solution of Ricci flow on a compact manifold on the time interval 0 up to capital T, where 0 is less than T is less than infinite. Then, if the curvature is bounded, i.e. the sup of the curvature tensor over the manifold cross the whole time interval, is uniformly bounded by some constant, the metric Gij of t converges smoothly to a smooth limit metric Gij of capital T as t tends to capital T, and the flow can be extended to some larger time interval, 0 up to t plus epsilon, for some epsilon greater than 0. Or to put it in very simple language, Ricci flow can be extended as long as the curvature is bounded. And another way to say it is that we have a blow-up criterion. If we have a maximum time interval, then of a maximum time interval of smooth existence, then at the end of that time interval, the curvature has to blow up. It cannot remain bounded. It's worthwhile formulating that as a separate corollary. discovery existence of maximum time interval suppose G naught is a smooth initial metric on a compact manifold, Mn, then Ricci flow ddt G equals minus 2 times Ricci of G of t has a smooth unique solution on some maximum time interval zero up to capital T, where 0 is less than t is less or equal than infinity. And if this maximum time interval, let's call it T max, if T max is less than infinity, then the maximum of the curvature on Mn cross time t is unbounded for t approaching capital T. So we have a blow-up criterion and we have a criterion for the length of the time interval where a smooth solution exists. Now, the proof consists of 3 parts. The first part, we show that if the curvature is bounded, then all the higher derivatives are bounded as well. From the assumption that the maximum of Riemann over Mn on the whole time interval is less than C0, we get that ddt of, say, gradient Riemann, let's first do it in the simple case first, is less than Laplacian of gradient Riemann minus 2 times the second derivatives plus, and now here it was a constant depending on n times C naught, because one factor here was the curvature times the gradient of Riemann squared. Remember, in this case, the first derivatives, we had a gradient Riemann quadratic, and then there was one factor involving the curvature, so we can estimate this factor by C0. Now, it is immediately clear from the maximum principle that by comparison with the ODE, where you have ddt f less or equal than some constant times f, that this can grow at most exponentially. So on a finite time interval, we immediately get a bound on the gradient of Riemann. Now this bound on the finite time interval is depending on the length of the time interval, which is not so pretty. So there's a simple trick how to get a bound which is in fact independent of the length of the time interval. It's worth remembering. So the trick consists in combining this inequality with the inequality that you get for the evolution equation of the lower order term, which is the Riemann tensor itself. For this, we get on the evolution equation of the Riemann tensor, obviously we get these two terms, and then Riemann had on the right hand side this quadratic term. So now, since we've multiplied with Riemann once more, the error term here is some constant, again depending on the dimension, times C0 cubed, because it's going to be a cubic term in the Riemann tensor, and if you look at scaling, this is exactly right. So now you see here there is this good term, which is exactly of the same order as the bad term there. So if you choose a function f to be the gradient of Riemann squared plus enough of Riemann squared, where enough means that this number n should be, say, as big as this number Cn times C0, then we get that ddt of f is less than the Laplacian of f. And then let me throw away this term here, and I get minus 2 gradient Riemann squared times n from the good term here, plus the bad term Cn times C0 gradient Riemann squared. And then I pay for this with this bad term here, but this is lower order, plus n times Cn times C0. And you see in this evolution equation here that this term swamps the other one. So in fact, I have, with this choice, I have one term left over because I only need one of them. So I have this negative term here left over, and this bad term there, which is lower order, cannot hurt if this gets too large. But this term here, in turn, is dominating f. So from here, you see immediately that the function f at the maximum of f on Mn cross time t will be less than either the initial data or some multiple of this number here, or this should be a C0 cubed, or some multiple of and some C0 cubed. C tilde n times C0 cubed. And this immediately implies that the gradient of Riemann is bounded in terms of the curvature. Okay, now we have bounded the gradient of Riemann in terms of Riemann, and now we use induction again, and we can get corresponding bounds for all higher derivatives of the curvature. I'm not carrying out the details, but we can now use this inequality. We can use this inequality that we've established, and then the worst term here will again be the term where one of them is equal to n and the other one is equal to the curvature, because then we get something quadratic. So, and the other terms will be even lower order, so we can estimate this by Laplacian gradient Riemann squared minus 2 gradient n plus 1 Riemann squared plus some term times gradient n Riemann squared, and all the other terms that come up. And this C tilde actually may depend on C0, right? So maybe I should write this. It includes the C0 term, and all the other terms can be used with Schwarz inequality to relate them to the curvature or lower order terms that have already been estimated. So let's write these extra terms C hat depending on n, and C0, because they have already been estimated if we are in an induction step where we already have bounds up to order m minus 1. So there C hat includes estimates on all derivatives up to order n minus 1. Now, now we are in the same situation as before. We have one such bad term, and now we deal with this bad term by adding in a lower order term. So then, as before, consider f to be gradient n Riemann squared plus enough of the previous derivatives and just like before, in the case of n equals 1, we conclude that d dt f will be less than the Laplacian of f. And then if the n is sufficiently large, such that the Bochner term coming from here, that's the good term, 1 but with n plus 1 replaced by n, cancels this one, then we will be left with some, say, half the Bochner term, so we will have minus gradient m Riemann squared will be left over, and we pay for this with n times the C hat of n, m, and C naught. And now we are exactly in the same situation as before. The dominant term that's not yet bounded in f is this one, and now this will be bounded by either the initial data or the maximum such that this term on the right-hand side is still non-negative. So we get that f, the sup of f over mn cross 0t is bounded by the maximum of the initial data, mn at time 0, or a constant, let's call it c bar, depending on n and c0, given by these two terms here. Okay, so as an upshot, we get that for all n greater or equal than 1, there exists some Cn such that gradient m of Riemann squared is uniformly bounded by Cm less than infinity on the whole manifold and the whole time interval. Where Cm, of course, depends on C0, the curvature. Okay, so we have all higher derivatives. Now, the aim is to use Arcela-Ascoli to get a smooth limit metric at this final time, capital T, and then use the short time existence to keep going. But we have to first show that we actually get a metric as T approaches capital T. So we have to look at the evolution equation of the metric for a moment. Show that that converges. By the way, we will later see that the gradient estimate I just proved is in no means optimal, right? It's not scaling invariant, it's not interior in time, it's not interior in space. It can be improved a lot, but I think here I just focused on a dirty, quick proof for the higher derivatives in order to prove this theorem. So the second step involves the metric, and for that I prove a little lemma that was first stated by Richard Hamilton, and it says that if G of t is a family of metrics on Mn, say, solving ddt of g ij of t, this derivative, this integral dt is less than some constant that I again call C0, has nothing to do with the other C0, less than infinity. Let's call it C1. So suppose we have a family of metrics that just satisfy this estimate. Then, I shouldn't say solving, that's satisfying. Has nothing to do with solving a particular evolution equation. So suppose you have a family of metrics that satisfy such estimate on the time derivative, then all metrics G of t are uniformly equivalent other words, there exists some delta 1 such that the length of some vector theta with respect to the metric g of t can be estimated from above by delta 1 to the minus 1 times the length of this vector with respect to the initial metric, and also can be estimated from below by the length of this vector with respect to the initial metric. So they are uniformly equivalent. The eigenvalues are uniformly bounded above and below by some multiple of the eigenvalues on the initial metric. And Gij of t converges uniformly to a continuous metric g of capital T as t approaches capital T. And by the way, capital T here is allowed to be infinity. And the proof just checks how the ratio between these lengths of a given vector changes. Let theta be given, and then we compare the logarithm of theta at time t, length minus the logarithm of theta at time 0, or say time s, you can take any time here. And then this is obviously can be estimated from above by the fundamental theorem of calculus by the integral from s to t of the derivative of Gij. Notice theta is fixed. Theta is fixed, so when I estimate theta squared, I just get ddt of Gij times theta I theta j divided by theta squared, so this cancels out, so I just get this. And this length is taken with respect to g of t, I should have said. And this is uniformly bounded by assumption. But then this means the logarithm of the ratio between the two lengths is uniformly bounded above and below. So this inequality here is valid if we choose delta 1 as e to the minus c1. Star follows with delta 1 equals e to the minus c1. And once we have that, it's also clear that we get a Cauchy sequence in the length of theta squared as t approaches capital T. So also we get that theta squared of g of t converges uniformly to a continuous function, this positive function, which I call theta squared at capital T. And now, once you have the squares of a the pure squares of a bilinear form, convergence, then you can use the polarization identity to get the other components convergence. So note that for any bilinear form, G of VW is the same as 1/4 parallelogram identity of V plus W squared minus V minus W squared. And therefore, we get, since all the squares are converging, we get that the Gij of T converges uniformly to Gij of capital T. And this proves this little lemma. Notice that in particular for t tending to infinity, if capital T is infinite, then this is delicate. You would get in many evolution problems quite easily that the time derivative of the metric decays like 1/t. Think of it in the case of Ricci curvature, for example. Ricci curvature scales like 1/t, so the estimate 1/t would be very natural for a long time for the right-hand side of such an evolution equation. But 1/t is exactly not enough to make this lemma work. So even though you have proved some natural decay, it doesn't mean necessarily that it's enough to get a limit metric. So the lemma is rather sharp. Now, to conclude the proof, we just have to recall that also the Christoffel symbols are satisfying the evolution equation that has curvature or gradient of curvature on the right hand side, and since we have all these higher derivatives bounded, it means that the Christoffel symbols are under control as well. So if we have the metric converging, the Christoffel symbols converging, and so we conclude we get a limit metric. And since we have all the higher derivatives of the curvature estimated, we get a smooth limiting metric. So step 3, since ddt of Gij is equal to minus 2 Ricci Ij, which is less than the constant depending on n times C0 by assumption, and since ddt of the Christoffel symbols are bounded by some terms involving gradient Ricci, which is also bounded by some constant involving n and C0 by our gradient estimates, and since we have all the higher derivatives of curvature bounded, all this together implies that Gij of T converges to a smooth Gij capital T. But once we have a smooth Gij capital of T, then use the short-time existence result to get a solution of Ricci flow on the interval t plus epsilon for some epsilon bigger than 0, depending on the norms of Gij capital T. But this solution on this extra small time interval is an extension of the old solution on the previous time interval, because all the metric and the derivative of the metric are smooth and match together at capital T. This extends the solution on the earlier time interval, since the derivatives, the metric and ddt of the metric match at t equals capital T. And this proves the theorem. Now, I would like to make a couple of comments. First of all, the corresponding result for mean curvature flow would be very analogous. So remark what for mean curvature flow where we have ddt of f equals mean curvature vector, they can compute that ddt of the second fundamental form is Laplacian second fundamental form plus second fundamental form times second fundamental form norm squared, which, as I said before, is it's exactly the same scaling, really. Just keep in mind that the Ricci tensor scales like the square of this. And then you would have the fourth power of A, which is like the square of Ricci or Riemann tensor. So it is the same scale. Just have to keep in mind that this scales like the square root of curvature, or square root of intrinsic curvature. So from this, you can get an inequality on the higher derivatives of the second fundamental form, which looks very much like the one that we just had of the higher derivatives of the Riemann tensor. So we have sort of the leading terms exactly the same, the Bochner term here. But then here you get, because of this slightly different setting, you get instead of 3 terms, you get 4 terms. One of them is, of course, the simple term coming from the fact that you're differentiating the square here. And then you get 3 terms with varying derivatives of the curvature. But now you get it in such a way that I plus j plus k is equal to n, which again would agree also with the 0 order term. And then the proof proceeds in very much the same way. Note that this time ddt of g is less than a constant times curvature squared, and ddt of the Christoffel symbols is less than a constant times gradient a times a. So the proof proceeds then in a very similar way as before. That's comment one. Then the second comment I want to make is that so we have the same assumption here. As long as the curvature is bounded, our lemma says that the induced metrics are uniformly equivalent. So the solutions of mean curvature flow maintain a induced metric which remains a nice Riemannian metric, which means that the map giving the solution of mean curvature flow remains a nice diffeomorphism. And this is exactly what is not true if you look at the harmonic map heat flow. So there is a big difference to the harmonic map heat flow, where you have a map between some Riemannian manifold and another Riemannian manifold satisfying something like Laplacian with respect to the fixed metric and the target metric of U. I don't want to go into the details, but this flow is not preserving diffeomorphisms. So this does not preserve diffeomorphisms. So one of the main motivations to study mean curvature flow and Ricci flow is that you can stay inside the class of diffeomorphisms, which you cannot do with harmonic map heat flow. Okay? So that's one very important point. And the third comment I wanted to make is that several improvements are possible so the one can get short time existence under weaker assumptions, but rather than smooth metric, we can assume maybe something like just bounded curvature, or even less. Maybe we just need a smooth background metric, e.g. existence of a smooth equivalent background metric. And that means there may be other weaker or more precise blow-up criteria. For example, in the case of mean curvature flow, it is enough to know that the thing is a Lipschitz graph over some nice given hypersurface. So instead of bounded curvature, you need sort of a somehow bounded by Lipschitz norm. Similarly, it is enough for Ricci flow to assume something about the existence of a smooth background metric and some relation to that background metric. I will not cover this part of the course. I just want you to know that there are such improvements, and they have to do with improved regularity estimates for curvature terms, for the Christoffel symbols and so on, which we come back to later in the course. Thank you for today.